Hi, everybody. Okay, today what we're going to get into is we're going to get into solving systems. And that's a very technical term for something that's actually pretty direct. So when you take a look at the first instruction that you see on the page to solve the following systems by graphing, it's important for us to be able to recognize, what does a system mean? So can you just make a note on your lesson page that what we're talking about when we say a system simply means multiple equations. So that's all that means. And so you can now kind of see why in problem A you have two different equations. That's all a system refers to. So anytime you see, hey, a system in the future, that's a mathematical term that means multiple equations. There's no limit to the number of equations that you have in that system. What we're going to focus in on are systems of two equations. And what we're going to do is we're going to solve them by graphing. So, without any discussion really as to what it means to solve a system, what I'd like you to do is to graph both of those lines on your grid. Now, in order for us to talk about these properly, then what we do is we number our equations. So you're going to see me put on a 1 and circle it to denote equation 1. Mathematically, if you see a number in a circle, then that's a universal notation for an equation. So now the whole world knows that we have equation 1 and equation 2 because of how they're labeled. So what I'd like you to do is to go ahead and graph equation 1 and graph equation 2. Use any method you would like to graph, and then stop there. Okay, so let's pause the video and use this as a little bit of a check. Okay, we're back. So I'm going to match up with the colors that we have. I've labeled the first equation in purple, so I'll graph it in purple. Because of the way it's written, then maybe I go slope-intercept. So I have a y-intercept at -2 and a slope of 2. So I'm to the right one up 2, to the right one up 2, so on and so on. And I could keep going through with that. That would be me graphing my line. And we are so good at that by now that I'm hoping that we're hitting that benchmark of like about 20 seconds to graph using that method. I'll label my line. There's graph 1. Okay, graph 2. I would have had a bunch of people that would have rearranged graph 2 and got the y all by itself and graphed using the same method. However, just for variety, maybe I had some people that wanted to graph by intercepts. So let's say I said, okay, my x-intercept means my y value equals to 0. So x plus 1 equals 0, x equals -1. And then maybe I said my y-intercept means my x value equals 0. And so -y plus 1 equals 0. And so y equals 1. Well, I can plot my x-intercept at -1. And I can plot my y-intercept at 1. Okay, those points are really close together. But if I go through and I connect those, well, it's really tough. So I'm going to keep putting on some points that would move according to slope, over 1, down 1, because that's what I have between those 2 points. Then I can connect those and extend it the width of my grid. And hopefully we get something like that as equation, yikes, not 20, 2. And there we go. Okay, for us to put down what that solve word means. What we talk about to solve now, and I need you to make this note, to solve a system, it's actually the easiest thing. I want you to find the point of intersection. That's really all it means to solve a system. Let's find out where both of those lines lie in the same position. It's so common of a process for us that sometimes you'll even see like POI putting in brackets at times. Find the point of intersection. So for us, we now have to look on our graph and we have to locate the point of intersection. And we should be good to locate that right there. There is where both of my lines cross, which means they both lie in that position. So how do you now actually solve? We just have to state our point of intersection. Okay, what are the coordinates at that point? 3, 4, and we are good. There you go. That's solving a system by graphing. We recognize the term system just means multiple equations. To solve by graphing means we produce a graph of both of those equations. And to solve it means find the point of intersection. Okay, let's jump into the next one, problem B. What I'd like you to do is to go through and solve the system in B. So I think we should be good to go start to finish on this one. Like even after one example, I think we should be pretty automatic. So I want you to go through and use the exact same formatting as what we did in problem A. And I want you to go through and solve that system. Okay, pause the video now. Okay, we're back. So maybe I have equation 1 and I'm going to switch to red. Maybe I have equation 2. Equation 1, maybe I just think about getting that y over there by itself. So equation 1 would be y equals 3x. Then I have to get rid of the 4 over there, so minus 4. So if I rearrange my equation into that form, then it becomes pretty fast to be able to say my y-intercept is then at negative 4, and I have a slope of 3. Over 1, up 3. Over 1, up 3. Over 1, up 3. So on and so on. Connect them and extend it the width of the grid. Make sure that we have that labeled. There's my equation 1. Same thing as before. I could have had some people rearrange equation 2. If you did rearrange it, then you probably have negative 2y equals negative x plus 3, and so y equals positive 1/2 x minus 3/2. Now you would plot your y-intercept at negative 3/2 and move according to a slope of 1/2. But again, just for variety, maybe I took equation 2 and I graphed that one by intercepts. So x-intercept means my y value is 0, so x equals 3. Nice. Point of 3. To find my y-intercept means my x value equals 0. And so that wipes out my x term, so I have negative 2y equals 3 and y equals negative 3/2. Negative 3/2 would be a 1 1/2, so I go down 1 and another half. Okay, connect my points. Oops. And now I extend that, the width of the grid. Label that graph. And we know to solve a system means to state the point of intersection. And so where do those points intersect? Right at that location. And that is at 1, negative 1. There we go. So hopefully we match up. And solving a system by graphing is pretty straightforward. It can be cumbersome, like it can be a little bit of work to take the time to actually graph both of those graphs. But in terms of difficulty, hopefully not too difficult. Okay, let's take a look at question 2 at the bottom of the page. What we want to do is we want to show algebraically. So, no graphs. That the answer we got in 1b is the solution to the system. That's basically us saying, hey, show that you were right. Show that that solution of 1, negative 1 was correct. Okay, I want to walk through this process because this is something that we addressed way back when we started to solve equations, is how can we check our answer? So what we are going to do is we're going to take the first equation, equation 1, which was 3x minus y equals 4, and what we are going to do is we are going to sub in our point of intersection. What we're actually doing is confirming, is the point 1, negative 1 on equation 1? Does equation 1 pass through that point? And the way that we need to prove that is to break that equation apart into the left side of the equation and the right side of the equation. Now, this is very important, that we can't keep the equation together. That is, we cannot keep it as 3x minus y equals 4 because we can't use the fact that it's equal to prove that it's equal. What we have to do is we have to break it apart completely. And that's what you see here. My left side is completely separate from my right side. And what I'm going to now do is test, does that value make my equation equal? So I'm going to sub in 1, negative 1, which means I'm going to replace my x with that x coordinate and replace my y with that y coordinate. Now I can go ahead and calculate whatever I have. So 3 times 1 minus a negative 1, I got 4. I take a look now, my left side equals 4 at that point. What does my right side equal? The same value. And that's what I need. I need my left side to equal my right side. And that has guaranteed that then that point is on equation 1, or equation 1 passes through that point. Now, that does not do the job of what the problem states. All we've proven at this point is that that green point, 1, negative 1, is on equation 1. The only way that we can prove that it's actually the solution to the system is to show that that point is on all of the equations. So I want to leave you with the second part. Let's go ahead and let's take equation 2 now, which was x minus 2y equals 3. And I would like you to do a formal check the same way as what we just did in equation 1. Okay, so I want you to go ahead and sub in that point, and we should match up in the end. Okay, let's pause the video now. Okay, so for you to work through this, I would need to see this exact same thing written on your page. The left side of my equation is x minus 2y, the right side is 3. Replace your x with what it's equal to. Replace your y with what it's equal to. Now calculate it. You don't need to show me 1 plus 2. We can jump straight down to here if we're comfortable. You have now shown that your left side equals your right side, and you have now proven that the green point is on equation 2. Well, now all it takes then is a little bit of logic to say that, yeah, well then, if my green point is on equation 1 and my green point is on equation 2, well, if that point is on both of those equations, then therefore 1, negative 1 is the solution. And there we go. That's how we can work our way through to check if we needed to check one of our solutions, but also to provide a formal check to test that solution. Okay, I'm assuming as we move forward then that you will be totally fine to solve systems by graphing. We should be comfortable to be able to graph a line by now, that we could graph multiple lines, find the point of intersection, we're good. What I want to start to talk about where we go next is some interesting things that can pop up when we do try to solve linear systems. So what you see at the top of the next page is a huge chart. And we're going to have a really big chart for us to go through. Now, I'm just going to scroll through that so we can see that on. There is our full chart. Now, what I don't want to do is keep scrolling during this lesson. And so what we're going to do is we're going to break up that chart a little bit. I just want to make sure that we're comfortable with what's in the chart. So the first thing we notice is I've given you a series of linear systems. You see that you have column A, column B, and column C. In each column, you've been given a system. For us to go through and fill in the chart, you need to be able to tell me the number of solutions that we have, the slopes of the lines, and you have to be able to give me the y-intercepts of each line, or y-intercept of each line. At the bottom, we're going to graph the system. That part we don't need to do. Some of us are going to want to do it because it's going to help us to give us a full picture, but I think we'll be okay. So, I want you guys to play around with this. And I want us to come up with the number of solutions, the slopes of the lines, the y-intercept of the line, without solving our system. Okay, that might be kind of a weird instruction. I totally get that for everybody, we could just go down and you could graph both those lines, you could solve the system, and therefore you could answer for the green, the yellow, and the orange. I want us to be a little better than that. And we need to tie together a couple ideas. So I'm going to ask you to fill this in kind of in a backwards way. What I'd like us to do is to go through and find the yellow and the orange first. So I want you to find the slopes of the lines and the y-intercept of each line in each column. So if we were to go all the way back up to the top, for instance, in A, you're going to say, I have equation 1 and I have equation 2. So down below, you're going to give me the slope of equation 1 and the slope of equation 2. You're going to give me the y-intercept of equation 1 and the y-intercept of equation 2. In B, you're going to give me equation 1 and equation 2, and we're going to do the same. So as you work your way through, that's how I'd like us to fill in this table. We are going to fill it in. Step 1, then step 2, and then I want you to try to answer the green. Okay, so we're going to hop around a little bit on this page. You might then be asking, okay, but why did you put all of this space in here? Because some of us might want to do a little bit of work to get there. I hope that we can notice that in column B, you cannot read the slope or the y-intercept from your equations because they're not in the proper form. And so maybe we need a little bit of space to do some rearranging of equations. Okay, I want to let you guys go, and the only thing I want you to focus in on right now, find the slope of the lines, find the y-intercept of the lines. Okay, let's pause the video now. We're finding those two properties for all three columns, all three systems. Okay, pause it now. Okay, so we're back. So what you'll notice is I've just zoomed in on the one kind of section of that chart that we're going to fill in. So, as we said earlier, we're starting off with maybe the slopes. Then we're trying to get our y-intercepts. And then maybe we're trying to come up with our solutions. So I would hope that for most of us, we were pretty good to be able to find the slopes of equation 1 and equation 2, because you can read the slope 2 and the slope -1 directly from both equations. I'm also hoping that we were pretty good at being able to come up with the y-intercepts of both. The y-intercept of the first, the y-intercept of the second, because we could read them from both. Okay, that should match up in our chart. However, now that we jump into column B, we notice that we cannot read those directly from your equation. Like, I can't read my slope directly from those. So maybe for column B is where we jump back up into our table, and then we had to do a little bit of work. So we're going to jump back up to the top portion of that table to do a little bit of rearranging. Okay, so what you see then is we just jumped back up to the top of that table. And in column B, I'm going to do a little rearranging. So if I take equation 1, I want to get the y all by itself. That means that I need to divide out my -3. And so as I divide out that -3 from everything on the other side, then I'm going to get a 6 divided by -3, which is -2. And a -2 divided by -3, well, a negative divided by a negative is positive. And 2 does not divide by 3 evenly, so there's my fraction, there's my x. Now, some of you won't like the look of that, and like, feel free if you want to or need to rewrite that with your x term first and then your y terms, or your constant second. But I'm hoping that we're good in both cases. Those are the same thing. Okay, I'm just going to clean up a little bit that's up in that equation, because now we can jump to equation 2. To get the y all by itself in that one's a little more direct. I just have to divide out a +3. So I get y equals 2/3 x minus 3. There we go. So hopefully that matches up with what we've got. And we would now be able to go down and complete the slope and the y-intercept. While I'm here, we might as well go through and do the same thing in column C. I've got a little bit more work in equation 1 because I have to get rid of that x term first, or since my y term has a negative exponent, I'm going to imagine it going over to the right side. It's going to be all by itself on one side. That means that I have to get rid of that 6 and have that be on the same side as the 4x. Now I could divide out my 2, and so I get a 2x minus 3. There is equation 1 in slope-intercept form. I could do the same thing with equation 2. I'm going to get rid of the +9, so I'm going to subtract 9. I'm going to get rid of a times by 3, so I divide by 3. And there we go. So what we want to do now is we want to jump back down to the middle portion of that chart, and let's fill in everything we know. And so what you see now is the middle part of that graph. But all I've done is I've just written those equations down just above the chart so we can see them clearly. So we should now be very, very fast to say that the slope of equation 1 in column B is 2/3, and the slope of equation 2 is 2/3. The y-intercept of equation 1 was -2, and the y-intercept of equation 2 was -3. We then have for equation 1 a slope of 2, equation 2 a slope of 2, a y-intercept of -3, and a y-intercept of -3. Okay, we get down to that point, And this is where I want us to really put on our logical hat. Like, I know it's going to sound weird, but like literally take your arms, because your arms can act as lines. And what I want us to do now is to examine that last row, us coming up with our number of solutions. Right? If we recall, the solutions to a system are the point of intersection. Then really what I'm asking in this case is not what is the solution, but I'm asking what is the number of solutions. So, how many points of intersection do I have within each system? So, let's use our arms a little bit. Take one of your arms and imagine it having a slope of 2. And put it in a location where there's a y-intercept of 1. Okay, let's take the other equation and imagine it having a slope of -1. And put it in a location where it has a y-intercept of 7. If we were to examine that, or even just think about that property, then I'm hoping that we were able to come up with one point of intersection. And I want us to jot down a couple quick things in our table. Do you notice that what you have here are different slopes? And I want you to imagine taking your arms, representing 2 different lines, and make them have any 2 slopes you like. And I hope that we could see that if your arms were long enough, like infinitely long, that eventually those 2 lines are going to cross somewhere. As long as they have different slopes, then they're going to cross somewhere. Okay, let's take a look in column B. Maybe we see something different pop up. Let's look in our table. Do we notice that once we rearrange those lines, they actually had the same slope? And we know something about lines that have the same slope. It means that they're parallel. Okay, so how many times do parallel lines cross? How many times would parallel lines intersect? And I'm hoping that we could have got to, there is 0 as my number of solutions, or like you could write that there's none. There are no solutions to that system. Nice. Okay, let's take a look at column C. That if we take a look in that slope column and we notice that we have the same slope, then we may go, hey, same slope, parallel lines, therefore none, and we would be incorrect. That we've got just enough knowledge to be dangerous. So let's get rid of that 0 since it's incorrect, because we actually didn't examine this far enough. Take a look at your y-intercept on your purple column, column C. You also notice that you have the same y-intercept. Well, if equation 1 has a slope of 2 and a y-intercept of -3, and equation 2 has a slope of 2, can we see that I actually gave you the same equation? That when you look back up at the original way I gave those to you, they're just kind of hidden that they were the same equation. So, since I gave you the same equation, then that means if you were to graph those 2 lines, they would lay on top of each other. So if I was to ask you your question again, what is your number of solutions? Well, how many times do 2 lines that lay on top of each other cross or intersect? And I would hope that you would give me an answer, like a word answer of like always. If they are the same line, then they're laying on top of each other, which means they're always hitting each other. Now, how do we state that mathematically? You would tell me that there are infinitely many solutions. Okay, so let's take a peek then at what made up the difference between the 0 versus the infinitely many. And it's the fact that we actually stopped short a little bit, even on the 0. Notice your y-intercepts in your column B. They're different. And so if we go all the way back to column A, and we examine column A, then as soon as I have two lines that have different slopes, they've got to hit each other somewhere. They've got to hit once. If I take a look in column B, and I have two lines that have the same slope, but have different intercepts, then that means they run in the same direction, but they lie in a different position, which means they never hit each other. So there are 0 solutions or no solution. Now we look at column C. If I gave you two lines that actually were the same line, they just look different because they were unsimplified. So they have the same slope and the same y-intercept. Then that means that they lay directly on top of each other, which means they are always intersecting with each other, or there are infinitely many solutions. So we want to be able to get to the point where without graphing, you could tell me whether there was 1, 0, or infinitely many solutions to a system. I hope that we're very good on the fact that nobody is asking about what about 2 solutions? Couldn't I have 2 solutions to a linear system? And I'm going to argue to you that if that was one of our lines, how are you going to draw another line that intersects that twice? If it crosses here, then it would have to loop around and cross here again. And as soon as it loops around, then it's not a line. And so I hope we see that it can't cross twice, 3 times, 4 times, 1,000,000 times. It can't cross 1,000,000 times. It can only ever cross once, never, or always. Okay? There's a big chart for us, and we need to be able to make sure that we can find all those types of solutions based on the properties of our lines. Okay, let's jump into an application problem. So let's look at that last page now. So here's a bit of an application problem for you. At Lowell High School, the cost to attend special events depends on whether or not a student has purchased a $10 discount card. So option A just says the student buys a discount card. The cost is $5 per event. So if you buy the discount card, then you're only paying $5 to go to each event. So let's say that it was like a school dance. If you buy the discount card, you only got to pay $5 to go. Or option B says the student doesn't buy a discount card, but they have to pay $7.50 for every event that they want to go to. Okay, you have 2 instructions in here, maybe 3 depending on how you look at it. The first thing that we need to do is we have to graph that relationship between total cost and the number of events. The second thing we have to do is determine the conditions under which you should choose each option. Now, where it says justify, I'm going to argue to you that determining the conditions, you always have to include justification for why you chose what you did. So really the justify is part of determine the conditions. So let's take it in its bits. You've got a grid on your page. Let's go ahead and let's graph that relationship. So what you'll see now is kind of a shrunken version of what you have. I've just put the details at the very top. We can go through and we can construct that. So what I want you to do is to go ahead and graph what option A would look like on that grid and what option B would look like. Okay, pause the video now. Okay, and we're back. So if I took the first case, then maybe I just say, the student buys a discount card. Well, that discount card is $10. So if they don't go to any events, they're going to have to pay $10 right off the top. And now every event that they go to is going to cost an extra $5. So if I go to the first event, then I got to pay another $5. Go to the second event, another $5. Third event, another 5, 4, and so on and so on and so on. So if I just get rid of all of that, then maybe what I did is I said, okay, and a 5, and a 5, and a 5, and a 5. And once I see the trend in that line, then I'm going to stop plotting points, and I'm going to connect them and extend the width of the grid. And there we go. That is going to be option A. Now, maybe we didn't graph it that way. Like, I could have had a bunch of people, like in me, I want to do this because I want to build an equation to something. That I take a look and I see, okay, I've got a C value on one axis, so my cost is going to equal, and I have an N on my other axis for my number of events. So it's going to cost me $5 per event with a fixed cost of $10. And we may have graphed that using slope-intercept. Like that is, you look at that and you go, well, there's your slope. There's your y-intercept, but since we don't have a y-axis, we have a c-axis. There's your c-intercept. So we would plot our point on our vertical axis and then move according to slope. Notice, though, this is not moving according to slope. Over 1, up 1, 2, 3, 4, 5. Over 1, up 1, 2, 3, 4, 5. Because we zero in, and I mean like we really pay attention to the scale on our y-axis. And notice that each grid line on your y-axis counts as 5 units. So for me to move according to slope, I would go over 1 and up 1 grid line. That's me going over 1 and up 5 units. So we got to be really careful on that. And I think you guys could see how you could fall into that trap. I'm just going to get rid of all that green so we can take that off our grid and block that out of our minds. Okay, now we take a look at option B. Option B says there's no fixed cost, but I'm going to pay $7.50 for everyone, which means that one event's going to put me right in the middle there. 2 events is going to be an even 15, and so on and so on. So if I connect all of those with a straight line, sorry, I just said it, with a line, then there is option B. And as I said earlier, it kind of screams at me to want to build an equation. So my C is going to equal, well, my variable cost now is $7.50 per, and I have no fixed cost. There would be my equation. Okay, so now the question asked, under what conditions, remember that's what it is, under what conditions, or determine the conditions under which a student should choose each option. I need you guys to know that there isn't really choice here. Like that is, you don't get the opportunity to throw opinion in this case. It has to be mathematical, and it requires us to go through and say, okay, I get the context. I want you to take a peek at how you graphed that. Look at your picture right now. And if I was to ask you, You planned on going to 2 events. Which option should you pick? I hope that we would all pick option B, because when you look on your graph, a cost of 2 events for option B is only that much. A cost of 2 events in option A is that much. I don't even have to calculate or look across to see, hey, how much is that? Because anywhere where I was lower would have to be cheaper on a cost axis. So the fact that my purple line is lower than my red line means I want to pick option B. However, what if I asked you, you planned on going to 8 events. Which option would you choose? Well, at 8 events, option A gets you something like this, and option B gets you something like this. Notice that it's flipped, that now option A is the cheaper way to go. So for us to go through, really what matters in this context is where do those 2 lines intersect? And maybe I say right there. Now, I do just want to draw to your attention that this is where human error comes in a little bit. That if I was to go through and try to label on my point of intersection, I would think that I was like somewhere in between 4 and 5, so maybe I'm like 4.5. And then across, I would be somewhere between 30 and 35, so maybe I said like 32.5. Maybe that was my point of intersection. I hope that we can see, though, that that isn't the real point of intersection. That it's where my point of intersection is based on a lot of human error. Like when I produce my graph, I have to be as accurate as I can be, but I'm still using a pencil, a straight edge, and I'm trusting my eyes. So that doesn't mean that I'm going to be perfect. I'm going to go based on where my lines cross. Now, maybe we can see that really my point of intersection should have been at 4:30. We can do a quick check. Take a look at option A. If I replace my n with 4, then I get 20 plus 10, that's $30. If I replace in equation B my n with 4, then 7.5 times 4 gives me 30. Look, I got the same. Therefore, 430 is on both graphs. Okay, but why didn't that show? Can you see that my red graph is actually a little sloppy? It's not perfect. Look at how I start to go above my actual points in there. So I'm going to ask you to be as super accurate as you can be. However, we have to go based on our graph. So I'm going to get rid of all of this stuff and get rid of my actual point of intersection. But I needed you to know that if your lines crossed at 4:30, you actually probably drew some pretty accurate graphs. Okay, according to mine, here's where the situation comes in. The question asks, under what conditions would you choose? Okay, so now I need to make a written statement. I would choose option A if, now I want to choose option A anytime the graph of A is below the graph of B. So I would argue then I would choose option A if I planned on attending, and since my point of intersection is at 4.5 events, and I can't go to half an event, then if I planned on attending 5 or more events, I would be good. So if I planned on attending 5 or more events. Okay, the question says determine the conditions under which you should choose each option. So now I would have to make a statement that I would choose option B if I planned on attending. Well, option B is where I'm going to want to go to that if its graph is below A. So where is my graph below? If I had planned on attending 4 or less, and sometimes we would say like 4 or fewer events. There you go. Now, I need to make sure that we're very good in terms of our wording and that we don't think that we're saying something that we're actually not. So, let's make sure that we're good. And I'm going to flip back to something. Take a look at how I just worded the last one. I would choose option B if I planned on attending 4 or fewer events. Are we good that if I had said fewer, or if I had said less than 4, that I would be incorrect? Because if I was less than 4, then that means I can't include 4. And according to my graph, at 4 events, my purple is just below my red. So we have to watch our wording a little bit and make sure that we're good. So let's make sure that we are very careful with where we use comparison terms. Now, let's imagine that I could go to 4.5 events. Or really what I'm trying to get at for those people who drew a really accurate graph, imagine that your point of intersection was at 430. Then you would tell me that your answer to the first one, I would choose option A, if you planned on attending more than 5 events. Sorry, more than 4 events. Your answer in the second option, you would choose option B if you planned on attending less or fewer than 4 events. What happens if you actually planned on attending 4 events? Are we good that you would actually have to say that that I am indifferent if I choose, or if I plan on attending 4 events? And that is, boy, about as sloppy as I could write. But I think I was able to fit it in on your screen for you. Okay? So there's a bunch of English in this last problem, making sure that we can interpret our point of intersection correctly. Okay, hopefully that gives you a little bit of context to how we can use systems to solve problems. We're good on the big chart on the second page about how we can identify whether there's one, no, or infinitely many solutions. And then obviously on the first page, are we good to actually solve a system? Okay, jump in, get some practice. Okay, good luck.